Today we will start microarchitecture, which is a fascinating topic that has fascinated many, many people in the world, and it keeps on fascinating many, many more people, especially these days. It's designing all these processors are all about microarchitecture. ISA is a little portion of it because ISAs don't change as much as we will see today. Okay, these are the readings basically for microarchitecture, and next week we're going to go deeper into microarchitecture and talk about improving the performance by pipelining. And we're going to cover a lot of issues on pipelining. Okay, so this is our agenda for today and the next few lectures. And then after next week, we're going to go into out-of-order execution. Basically, we're going to violate a lot of things that we said, which is the von Neumann model. Instructions are executed one by one in sequential order. We're going to violate that with out-of-order execution. We're going to execute the instructions out of their original order. Okay, but let's not jump ahead of ourselves. This is the von Neumann model that we discussed extensively last week, so you know that well. I'm going to go through it again today. This is the von Neumann machine, one of the von Neumann machines we discussed, LC3. We may discuss more of it, and this is the instruction cycle that you should know very well of. We're going to talk about how to implement this instruction cycle in more detail today. So it consists of fetch, decode, evaluate address, fetch operands, execute, and store result, right? And not all instructions go through all these stages. And we talked about the instruction set architecture. You know this instruction set architecture is an interface between the software and the hardware, what the software should expect and what the hardware should provide. We're going to go more into this. So what is microarchitecture then? Clearly, we see microarchitecture in this picture over here. It's right here. It's underneath the ISA. And as you can see, it's not exposed to the program. There's a layer between the program and the microarchitecture. That's the instruction set architecture. Essentially, microarchitecture is an implementation of the instruction set architecture. It's very simple. How do we implement the ISA? Basically, we will discuss this for many lectures, and that's called microarchitecture. And there can be many implementations of an ISA. ISA is really an abstract specification, right? You get this instruction, what should it do? But there, at the lower level, you have a lot of freedom to decide how to implement each instruction and each functionality. So clearly, there have been a lot of implementation of the MIPS ISA that you've been examining so far. MIPS R2000 was one implementation. It was a very simple processor, single issue, in-order execution, basically very similar to the von Neumann model execution that we're going to talk about today. But R10000 was a much more higher performance version of it that was essentially implementing the same ISA, MIPS ISA, but it was doing things in a different way, executing instructions out of order such that it was providing much higher performance. For example, Intel and AMD have implementations of the x86 ISA, which is very popular. And there have been many, many implementations of it. I don't even list 8286 over here, or the first Intel x86 processor over here. But even the younger ones are not the youngest ones today, right? And AMD has many other implementations also. So these are essentially implementing the same ISA. Now that's not absolutely correct because ISA also changed over time, but the core of the ISA is the same. There are extensions that are added to the ISA as you go from 1980s to 2020s, for example. Okay, so let's talk a little bit more on ISA design and trade-offs. Before I go into microarchitecture, I want to basically make you think a little bit out of the box, because it's important for you to think out of the box. And we're going to talk about a different kind of thinking. So you should know this very well. There are two key properties of the von Neumann model. What are those? Anybody can tell me? Hands? No hands? There are two key properties. One is actually written over there. It's a stored program computer. What's the other one? I know somebody knows, but maybe I cannot see the hands. It's a sequential instruction processing, right? Every instruction is processed after the previous one. So, stored program means that instructions are stored in a linear memory array, and memory is unified between the instruction and data. We've discussed this. And the interpretation of a stored value depends on the control signal. So basically, there's no distinction between instructions and data in the memory. Memory looks like bits. But how you interpret those bits depends on when you actually access those bits. If you're accessing the bits in the instruction fetch stage, you interpret them as instruction bits, right? If you're accessing the bits in the data fetch stage, then you interpret them as data. So basically, at what point in the processing of the instruction you access memory depends on how you interpret the bits that are in the memory. So hopefully this is clear. We discussed this before. But sequential instruction processing, which you should know next time I ask, is critical to the von Neumann model. Basically, one instruction is processed at a time, and program counter, the instruction pointer, identifies the current instruction, right? So that tells you what is the current instruction that you're processing right now. And it's advanced sequentially. You go to the next instruction after you finish the current instruction. You increment PC by 4 in MIPS, by 1 in LC3, right? Except for control transfer instructions, which basically take you to some other place so that you don't have to go sequentially, so that you can implement various forms of control flow like while loops, do while loops, for loops, if else, and if statements, right? Or case statements. Okay, so should definitely remember these properties. They may come later on. And this is essentially, if you look at the von Neumann model of a computer, you have a control unit that dictates everything. You have this instruction pointer. You go through this instruction pointer sequentially so that you can execute a program. Okay, so I'll ask you the question. Is this the only way a computer can operate? Is this the only model that we can have? Anybody? Yes, no? So by now, yes?
Well, obviously not, because otherwise you're going to have parallel programming classes.
That's true, yes. But if you look at parallel programming, yeah, you have multiple of these things, right? But if you look at multiprocessors, they're essentially, each of them is a von Neumann machine that are communicating with each other. Yes?
Is it GPU also like this?
Well, we'll cover GPUs later on. Yeah, so basically, I think you're getting at the right answer. Now that you're warmed up, you can give answers. Yes, you have.
At least when the unified memory thing was highlighted before, then that's obviously a different way to do that.
That's right, exactly. Yeah, but I want a much more completely different model. But I think you're all right. Basically, this is not the only way, but I'm going to propose a radically different way, which is also important. So basically, the answer is no. And we're going to see many examples of how to look at different models. But there's a qualified answer. No, but it has been the dominant way. Basically, even if you look at multiprocessors today, each thread is obeying the von Neumann model. Basically, when you look at the execution sequence of a single thread, it's the same as von Neumann model, as exposed to the programmer. Right? Underneath, we can do many things, as we will discuss. But let's take a look at a completely different way that's potentially exposed to the programmer. Well, I'm going to skip that. So in von Neumann model, the instruction is fetched and executed in control flow order. It's specified by the instruction pointer. So everything is sequential except for explicit control flow instructions. So in a completely different way, I'll call it as the Dataflow model, there is no program counter. We get rid of it. An instruction is fetched and executed in what's called the Dataflow order. Now, what does that mean? That means when its operands are ready. You somehow figure out when an instruction's operands become ready, and at that point, you fetch the instruction, and then you execute it. Sounds cool, right? There's no need for the program counter. And this is a potentially much more parallel model because many instructions can become ready at the same time based on the availability of data. As I said, there is no instruction pointer in this case. Instruction ordering happens purely based on how instructions depend on each other based on the data flow, right? So each instruction specifies which other instruction should receive the result. You're doing an add. Maybe the result of that add is needed by a future multiply. And this add instruction specifies that the result should go to this multiply. And that multiply instruction specifies that the result should be stored in memory. So it's basically, that is the input to another instruction that's a memory operation, okay? And an instruction can fire whenever all of its operands are received. Make sense? So that's how you execute. There is no program counter that dictates, okay, you should execute this instruction now. Once you're done, go to the next one. Once you're done, go to the next one. So there is no sequential element over here, except for data flow. So data flow is the only thing that dictates ordering. There is no sequential control flow-based ordering. So as a result of this, potentially many instructions can execute at the same time, right? And people have actually examined this model since 1970s, and we're going to talk about that later on also. So, but let's take a look at the differences of it. So this is a von Neumann program written in some sort of language. You don't need to know exactly what it looks like. In fact, it's hard to decipher, but you can easily figure out that you're adding this instruction is adding two values, storing the result in temporary place. This instruction is doing this multiplication, storing the result in the temporary place, and you get v minus w and v plus w, and then multiply them and store the result in z. It does something. So what is the significance of the program order? I'll ask you this question. You may think about that for a while. What is the significance of the storage locations? It's good to think about that also. Some of these are actually really temporary storage locations, right? You basically store the result in v and w, and then you use them, and then maybe you don't need them again, right? So in a sense, those storage locations are there just because you need to specify them. But maybe they're really used for communicating the result of this instruction to this instruction that needs that result, right? Basically, v and w are communicated to this instruction. So data flow means that you communicate the results between the instructions. So an example data flow view of this program would look like this. So in this case, we don't have an implicit sequential ordering, right? I actually put things in parallel with each other, as you can see. You have inputs A and B coming into this data flow graph. And graph is very intuitive. You can see that they're being added, B is being multiplied by 2. The result goes to this minus node and plus node, and this result goes to this minus node and plus node. And the results of these nodes go into this final multiplication node, and the result comes out as Z. So it's called the data flow graph. Each node in the graph is an instruction. Each arc in the graph is a value. It could be an input value, or it could be the result produced by an instruction. And whenever a value gets generated, you have a token on that arc, and an instruction fires or gets fetched and executed whenever all of its tokens are ready. For example, this instruction gets executed whenever A and B are ready. In this case, that's the beginning of the program. You supply the values, and this instruction gets executed. This instruction gets executed when the result of this is ready, and when the result of this is ready at the same time, because both of its inputs are ready, so it can fire. Okay? So multiple instructions can fire at the same time, concurrently. Of course, you need to have the hardware to be able to do this, right? Okay. So which model is more natural to you as a programmer? Would you program in the von Neumann sequential manner or the data flow manner? Who says von Neumann sequential? Okay, who says data flow? Okay, that's usually the case. Maybe this is a matter of nature versus nurture, because usually we learn programming this way, right? Not necessarily this way. Yes?
An FPGA be seen as a data flow view?
Yeah, you can certainly use the FPGA to implement something like this. It's a very natural fit. But you can also build a von Neumann architecture on top of the FPGA. It's a very it's a flexible substrate. Yes, very quickly.
When doing the calculations in the data flow model and you do parallel, would you need multiple ALUs to do that, or just one?
So, okay, anyway, let's not get ahead of ourselves, but yes, you need multiple ALUs, absolutely. So if you would like to be able to do this calculation in parallel, you need multiple ALUs. We're going to get to that later on. Okay, so but this is a very different model, right? As a programmer, you can certainly program this way also. And now, that's a different way of designing an ISA. It has implications on the microarchitecture also, as your colleague pointed out over here. Maybe you need to actually have multiple ALUs. Maybe you don't. If you don't, maybe you don't exploit the benefits of the ISA. Okay, so as I already said this, basically in a data flow machine, a program consists of data flow nodes, and a node fires, it's fetched and executed when all its inputs are ready, when all its inputs have tokens. So this is one example. This is a data flow node, and it's a potential representation in the instruction set architecture. Very similar to the instruction formats that we've seen. You could have an instruction format that is an opcode that basically has argument 1 and argument 2, where it's coming from, and then whether the argument is ready or not, and the destination of the result, where the destination should go to, right? Which instruction should receive this. Okay, so you could actually build many different nodes. So this is a conditional node, for example. Let's take a look at this. This basically, what this does is, it has two inputs, data input, X, control input over here. And it basically fires when both its inputs are ready. Of course, you need to have the data in the control. And what it does is, if the control input is false, it takes the data input and sends it out of this output. If the control input is true, it takes the data input and sends it out of this true output over here. Basically, this is where you can actually decide where to route the data. Do you send it to this instruction or this instruction? Basically, if the input is true, execute this instruction. If the input is false, execute this instruction. That's what happens over here. Basically, that's how you can implement an if-else construct with this graphical language, right? And in this case, because the input, control input is false, the data input goes out of the false output over here. Relational is another example. How do you generate the true and false? Basically, this is a comparison, greater than comparison node. It basically checks whether the left input is greater than the right input, and it fires when both of them are ready, and the result is essentially true or false, depending on whether or not this equation evaluates to true or false. In this case, it's true. 10 is greater than 7, so you get a true token out. I'm not going to cover the barrier synchronization. You can think about that. We're not going to use that, but that's another example, basically. What this does is it delays sending all of the tokens until all tokens come to this node. Okay, so let's have some fun with this program. Now that you've seen some examples, can you guess what this program does? Assuming, so let's take a look at this program a little bit. So n is a non-negative integer. This is 1. So initially, the value of the token over here on this arc is 1. The token on this arc is n. And what we have is essentially a very simple data flow program. What this programmer decided to do is copy n. This is a copy node. Basically, you get n over here, and then n over here, and then greater than 0 node. If n is greater than 0, you get true, otherwise you get false. And then you copy that Boolean value to here and here. Now, if this is true, 1 gets passed over here, otherwise you get the output over here. So there's an interesting thing that's happening over here at the end of the loop, let's say over here. The value of 1 gets replenished. So once the token is consumed, you can actually put another token onto this arc over here. That's a similar thing happens over here, as you can see. So basically, this is the output of this function. Let's call it function, call it a function. And you get the output at some point. Internally, there's something else happening over here, as you can see. We've copied n over here. Oh, this is true or false, right? Now, if this is true, n gets copied over here, and then n gets copied over here. So basically, what's happening over here is you get this input coming down, and then n coming down. You multiply 1 times n, and then you decrement n by 1. So, okay, did I give you enough hints? Can anybody guess what this program does? Yes? Absolutely, yes. It does calculate n factorial, and if you guys think about it, you'll also find it. Basically, that's what it does. You have 1 times n over here in the first iteration, and then n minus 1 goes here, right, in the second iteration. And then basically you check if n minus 1 is greater than 0. If that's true, you would multiply whatever came out over here with n minus 1. And remember, what came out of over here was n. So you multiply n with n minus 1 coming here. So now you have n times n minus 1. And then you circulate it back over here. Now you calculate n minus 2 over here. And then n minus 2, you check whether that's greater than 0. If that's true, you multiply n minus 2 with whatever came over here, which was n times n minus 1. So basically, n times n minus 1, n minus 2 gets over here. So you keep doing that until n is not greater than 0. So what happens if n is not greater than 0? This evaluates to false. If this is false, when both of the tokens are ready in this branch over here, the data input is sent to the output. And remember, if we actually go through this, we would get n times n minus 1 times n minus 2 dot 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 1. Right, that's the multiplication. So that's our output, n factorial. And if this is false, this copy node evaluates to false, the token that's coming out over here basically is sent to ground. So of course I didn't explain you the ground over here, but basically it gets rid of the token over here. And there's no token that's circulating in the program, and the output is sent over here. And there could be some other data flow graph that will consume this output, right? So your entire program may be much bigger than this. It can take this m factorial and input to some other function over here. Okay, so this may be a bit hard to see from the back especially. You can study it on your own. But essentially, this is a data flow program. We didn't really do any sequential programming over here, right? It's completely, well, this may not be the most completely parallel way of implementing a factorial, but it's one way of implementing factorial in a data flow ISA. And again, the principles are very simple. A node fires when all of its inputs are ready, and there's a specification of what the node does, and basically, eventually you get tokens out of this program, and that's the result that you get. Okay, any questions, quickly? No? Okay, have you seen the data flow model before anywhere? Probably not. Okay, so hopefully this is some eye-opening. We'll get back to this later on. Because this is not the way, not the common way we program today. The common way we program today is one Neumann model because we can reason about it more easily. There are some languages that operate based on data flow principles, but no instruction set architecture is able to do this today. This doesn't mean that it's not possible. It's possible. People have tried, and they failed. But what didn't, they failed because it was very difficult to build a software stack on top of it. Maybe that'll change in the future. But what didn't fail is underneath the principle that I showed you is actually employed in the processors today. So out-of-order execution is all about doing this without exposing it to the programmer. So basically, if you think about an out-of-order execution engine, it's actually operating in a very similar way without actually you knowing it as a programmer. The programmer programs like this. Underneath, the out-of-order execution engine converts that program to this and then executes it in parallel. And we will see that in like four lectures. Okay, so let's pop the stack a little bit. ISA level trade-off. Do we need an instruction pointer in the ISA? If you're a designer, architect designing an instruction set architecture, you could say, yes, I want control-driven sequential execution. And if I make that choice, an instruction is executed when the instruction pointer points to it, an instruction pointer automatically changes sequentially, as you know. If you say no, one way of saying no is you do data-driven, more parallel execution, and instructions executed when all its operand values are available. And there are many trade-offs associated with it, which we will not go into right now. But ease of programming, which one's easier to program, which one's easier to write compilers for, sequential might be a bit easier. Performance, which one's better at extracting parallelism out of the same piece of code. Hardware complexity, which one's more complex. There are actually a lot of trade-offs. As I said, a similar trade-off can be made at the microarchitecture level. So ISA, again, specifies how the programmer sees the instructions to be executed. But microarchitecture, on the other hand, is how the underlying implementation actually executes the instructions. It may have nothing to do with how the programmer sees the instructions to be executed, as long as microarchitecture reports to the programmer the order that the programmer expects. Right? So there are two choices. Programmer sees a sequential control flow execution order versus a data flow order. But microarchitecture underneath can execute instructions in any order as long as it obeys the semantics specified by the ISA when making the instruction results visible to the software. And we will see this many times. So programmer should always see what he or she expects, right? The order specified by this book, the contract, the hardware-software interface, the ISA. Okay, so we will get back to the von Neumann model, and we will assume von Neumann model for the rest of this class. But if you want to learn more about data flow, you can read some of these seminal papers. This is where it was first introduced in 1974. Or we will see that again in a later lecture, actually, when we talk about out-of-order execution, but we will see it at the microarchitecture level. And if you're really impatient, you can actually watch some of more advanced lectures. So let's get back to the von Neumann model. This is sequential execution. And all major instruction set architectures today use this model, actually. Even GPUs, somebody mentioned GPUs. If you look at a single thread, it's sequential execution. But there are many threads that are executing in parallel, as we will see in some number of lectures. So you can see the names of the ISA. Some of them you may be familiar with. RISC-V is one of the popular ones today. It's also von Neumann. RISC-V is actually very similar to MIPS. So underneath, at the microarchitecture level, the execution model of almost all implementations or microarchitectures is very different. So, for example, Intel 8486 was one of the first to do pipeline instruction execution, which you will see next week. Pipeline means you don't wait to finish this instruction before you start executing the next instruction. You basically pipeline. It's like an assembly line, right? When you're producing a car, you don't finish one car and then you start the next car, right, in a factory. You pipeline the production of the car. Parts of a car gets complete, and then you start the next car. Parts of that car gets complete, and you start the next car. It's a pipeline. But that's actually against the von Neumann model, but the programmer doesn't see this. Right? You can do multiple instructions at a time. You can do out-of-order execution, and we will see these. And you actually separate instruction and data caches, as one of you mentioned, breaks the von Neumann model also, because you have separate pieces dedicated to instruction and data. So basically what happens underneath that is not consistent with the von Neumann model, what is exposed to the programmer, is not exposed to the software. That's the key. So that's the difference between ISA and microarchitecture. Microarchitecture is what happens underneath. So you can read these definitions, I think, yourself. But basically, this is the computer architecture. When you think about computer architecture, there are two kinds of definitions. The traditional definition is this one, which was actually provided by Gene Amdahl over here. Basically, the attributes of a system as seen by the programmer, as distinct from the organization of the data flow and controls, the logic design. Basically, there is a distinction. Implementation is not seen by the programmer, but the attributes that are seen by the programmer is the architecture. Sometimes we talk about computer architecture that encompasses all of it. Okay, you can read this. I don't want to go through reading this. So basically, ISA is the agreed upon interface between software and hardware. Microarchitecture is a specific implementation of an ISA, not visible to the software. Microprocessor is, usually when we talk about a microprocessor, it contains the ISA, microarchitecture, and the circuits. And when you hear architecture, it's usually instruction set architecture plus microarchitecture. So let's take a look at some examples of this. This is actually, your homework contains some of this also. What is part of the ISA versus microarchitecture? Let's go through the analogy of cars again, right? Probably everybody drives cars here. You've used the gas pedal, I assume, if you drove a car. And that gas pedal remains very similar across many cars, right? That's an interface. Underneath, how you implement the acceleration, what happens when you press the gas pedal may be different, completely. You may have an electric engine underneath, you may have a mixed electric combustion engine underneath, or whatever. So basically, the internals of the engine is what implements acceleration, and that's really the microarchitecture of the car. Whereas all of the interfaces that the user gets exposed to is the architecture of the car. And microarchitecture may be completely different from architecture. Okay, and I've said this before. So in example, you have the add instruction. Pretty much all ISAs have similar add instructions. And your adder implementation may be completely different underneath, right? You could have a bit serial adder. We discussed, you basically add one bit at a time every clock cycle. If you want to do a 32-bit addition, it takes 32 clock cycles. Or you could have a ripple carry adder that basically adds all of the bits at the same time, but the carry needs to propagate, ripple, through the full adders. Or you could have a much more sophisticated carry look-ahead adder, which you can get to know of if you're really interested by reading this chapter over here. That's faster. So basically, there's a trade-off that you have at the microarchitecture level. How do you implement the adder? As long as it specifies what the add instruction is supposed to do, you're correct architecturally. Microarchitecturally, you can implement things to optimize speed, energy, performance, power, whatever you would like to. As a result, the ISAs have many implementations. And microarchitecture usually changes faster than the ISA. There are few ISAs, but many microarchitectures over the years. And this is because the interface is exposed to the software. Whenever you change the interface, for the software to take advantage of it, everything involved needs to change. Right? The compiler needs to change, the programmer needs to change, they need to become aware of the change, first of all, and that takes a lot of time. And if you actually make not a good change at the ISA level, people may not use it. That's why ISA designs are very careful in terms of changing the ISA significantly. Okay, so what does ISA basically? What does ISA specify? It's essentially what's in the manual. This is an Intel manual example. And we already covered a lot of this, but certainly we talked about instructions and memory. But there are other things that actually are specified by the ISA, like how interrupts and exceptions are handled, how do you do access control, how do you do I/O, how do you do task or thread management, power management, thermal management, multi-threading, multiprocessor support. We're not going to cover these, but be aware that these things need to be exposed to the programmer or the system software designer, some sort of programmer, right? If you're designing operating systems for an architecture, you need to know how does the architecture treat the multiple threads or multiple processors. Okay, so microarchitecture is the implementation of the ISA under specific design constraints and goals. Anything done in hardware without exposure to software. Again, this is a laundry list over here. We're going to see some of these, but a lot of systems today, for example, do voltage frequency scaling. They basically change the voltage and the frequency of the processor depending on how the system is used to save power, for example, or to accelerate an application. So if you may know of the turbo boost feature in Intel systems, they basically increase the voltage and frequency of a single processor if you're running a single thread, so that you can execute that thread much faster. Now the question is this a part of the microarchitecture? Is this a part of the ISA? If you want to answer that question, then the question you should ask is this exposed to the software, or is this not exposed to the software? That's the key question you should ask. If it's not exposed to the software, what does that mean? That means that, is this basically written in the book? Is there a way for the programmer to change this? Basically, if the programmer is able to scale the voltage and frequency using some instructions, then that is part of the ISA. If not, if the microarchitecture automatically does this, you may know that it's doing it, but you cannot do anything about it at the program level, then that's part of the microarchitecture, right? So a lot of these things actually can be part of the ISA or part of the microarchitecture, depending on whether or not they're exposed to the programmer. Usually pipelining is not exposed to the programmer, but we will see some models later on where even pipelining is exposed to the programmer. Okay, so let's take a look at a couple of examples. Add instructions opcode, is that a part of the ISA or microarchitecture? Any guesses? Yes? That's part of the ISA, yes, because it's basically shown to the programmer. The programmer needs to use the opcode to write an assembly program. What about the adder implementation, bit serial versus ripple carry adder? Is that part of the microarchitecture or ISA? Microarchitecture, yes. This programmer doesn't really care whether it's a bit serial adder or ripple carry adder, unless in the ISA you have different instructions for them, right? Which is possible, but today's ISAs don't do that. Number of general purpose registers, I'll give these to you. Basically, this is part of the ISA. The assembly programmer needs to know the number of general purpose registers to write programs. Number of cycles to execute a multiply instruction. Maybe a bit tricky, but this is really part of the microarchitecture. Again, in the MIPS ISA, there's nothing that you should know about how many cycles it takes to execute an instruction to write a correct program. Number of ports of the register file, we will see these later on, but this is part of the microarchitecture. Whether or not the machine employs pipeline instruction execution, that's also part of the microarchitecture. Okay. So remember, microarchitecture is the implementation of the ISA under specific design constraints and goals. And we've covered design points briefly in the past, but design points is a set of design constraints and their importance that leads to trade-offs in both ISA and microarchitecture. So why do we have these different types of microarchitectures? Because we want to satisfy some sort of design point, right? So cost, performance, maximum power consumption, energy consumption, availability, reliability, time to market, security, safety, predictability, all of these form the design point of your system. And you need to choose the right components, assuming you fix your ISA, you need to choose the right microarchitectural components to satisfy these goals. And clearly, it's effort. And design point, in turn, is determined by the problem you're solving, the application space, right? The intended users and the market. And that's actually very, very useful also. For example, you may be designing processors for scientific applications, transaction-based applications, databases, data processing, networks, basically very, very different types of applications, and they may dictate your design point. And these don't end, as you can see, right? Genome analysis. Or you may be designing a processor that can execute all of them, right? Which is essentially what these are today, right? These are very general purpose processors. They can execute all these applications. That's why you have these different choices in microarchitecture. Okay, so you know this already, so I'm going to skip this. So really the soul of computer architecture is the trade-offs. ISA level trade-offs, I've given you a glimpse of it. There's a lot more over there in the ISA level, which we're not going to cover. We're going to go a little bit more into microarchitecture level trade-offs, but first we need to learn what microarchitecture is. And there are also system and task level trade-offs. How do you divide the labor between hardware and the software? So microarchitecture level trade-offs, what kind of an adder do you use is the microarchitecture level trade-offs. And computer architecture is really the science and art of making the appropriate trade-offs to meet a design point. I'm going to belabor one point, why art? So if you, I keep saying art, because it's really partly art, because you really don't know and cannot model the future really well. Basically, you're designing systems for even 3 months later. If you want to really truly make it a science, it's very difficult because you need to really model what happens within those 3 months. But we're designing systems actually that are going to be used like 20 years into the future, right? How do you actually make it a real science? It's very difficult. So basically you have new demands from the top, new problems being executed on this machine that was designed 5 years ago, literally. And I have new demands. There are new applications that are executing on this, and this is already way too slow for the purpose of those applications. And there are new issues and capabilities at the bottom over here that you may be missing, and there are new demands and personalities of the users also. Users are also changing, right? But basically the future is not constant also. So you have changing demands at the top, changing issues and capabilities at the bottom, and changing demands and personalities of the users. So there's an analog from macroarchitecture. I like macroarchitecture, as you know. I'll give you this analog very quickly. Basically, future is not constant in real architecture either, right? And there are many examples of this everywhere in the world. This is one example over here. You have a mill that's later used as a theater, restaurant, and conference room, right? How many people have been there? Related to Tief and Burnett, right? Basically, it was originally built as a brewery, and then converted into a mill, and then a cold store, and then nowadays it's completely different, right? The architecture is the same. The ISA is the same, somewhat, even that's changed slightly. But what it's used for, the microarchitecture, is very different. And in fact, internals change also. Okay, so another example, this is Kraftwerk, and you can see that the stuff that's internal is different. But outside, it looks like the same. Okay, so with that, let's go into microarchitecture basics a little bit. Now that we have an ISA, we've established what an ISA is, how do we implement it? Essentially, how do we design a system that obeys the hardware-software interface? I'll also give another aside over here, because there are many, many creative solutions that you can come up with. System can be solely hardware or a combination of hardware and software. Now, what does this mean? You may actually have an ISA that you expose to the programmer. Programmer writes code in that. Internally, you convert that ISA into some other ISA. This is called binary translation, for example. Or Java virtual machines do that. They actually take Java code, translate it into some internal ISA, and then you build a processor that executes that internal thing. So there's a layer. This is the ISA that's exposed to the programmer. That's the hardware-software interface. Well, not hardware-software interface, actually programmer system interface, let's say. And then underneath, you have this translation layer, which may be software or hardware, and you translate it into another ISA that gets implemented in the microarchitecture. So keep this in mind. You could actually play a lot of tricks. Actually, x86 ISA is a very complicated ISA. So all x86 processors are doing exactly what I described. Programmer writes x86 code. Hardware underneath translates that x86 code to something like MIPS. Something actually very simple. Not exactly like MIPS, but conceptually like MIPS. And then the underlying microarchitecture is essentially like a MIPS, like a microarchitecture, as we will discuss. So we will assume hardware implementation for most of the lectures, but you can play tricks. You can start with some ISA that you expose and convert it to something else. So basically, how does a machine process instructions? That's what we're going to cover. And we will assume one Neumann model. Forget about Dataflow for now. So what does this mean? Basically, you're executing an instruction. Before the instruction, you have some architectural or programmable visible state. You need to transform it or process it. And you need to transform that, processing the instruction basically transforms that state to architectural state prime. That's essentially what executing an instruction means. Basically, of course, this needs to happen according to the ISA specification of the instruction. And ISA specification of one Neumann model is sequential instruction processing specified by each instruction. Okay, so this process instruction step, we're going to go into detail, and we're going to implement process instruction step. Basically, ISA specifies abstractly what the architectural state prime should be given an instruction and the architectural state. Essentially, it's an abstract finite state machine, right? You have state at the beginning, you have instruction that needs to be executed, and you have state at the end. You can think of this as a finite state machine where the instruction specifies something abstractly combinational, right? So state is programmer visible state, next state logic is the instruction execution specification. From the ISA point of view, from the programmer point of view, there are no intermediate states between the architectural state and architectural state prime. Microarchitecture, on the other hand, implements how the AS is transformed to AS prime. Well, yeah. So there are many choices in implementation over here. So we can have programmer invisible states to optimize the speed of execution. You can have multiple state transitions per instruction, and we will see both choices. Choice one, this is called a single cycle microarchitecture. An instruction transform architectural state to architectural state prime in a single clock cycle. Okay, we're going to see this. It's not going to be very effective for various reasons, we will see. So choice two does this, basically. You take multiple clock cycles to transform architectural state to architectural state prime. What does this mean? In the first clock cycle, you do some stuff, you update some internal state that's not visible to the programmer. In the next clock cycle, you do some other stuff to execute the instruction. You update some microarchitectural state again that's not visible to the program. In the next clock cycle, you do some more stuff. And finally, when the instruction is done, you update the architectural state. So all of these intermediate states are not visible to the programmer, and you take multiple clock cycles to be able to do that. But the result is essentially the same. Architectural state is transformed to architectural state prime. This is called a multi-cycle microarchitecture. It takes multiple cycles to execute an instruction. And we will see an example of this also. So the most basic instruction processing engine essentially takes a single clock cycle to execute. You use only combinational logic to implement instruction execution. There are no intermediate programmable invisible state updates. So you take the architectural state AS, process instruction one clock cycle, produce AS prime. So you can think of this as what we've seen in the past, right? This is essentially sequential logic. You have state over here, which has architectural state. You execute the instruction with some combinational logic, and then the instruction produces architectural state prime. And a processor is essentially consists of combinational logic that can implement all possible instructions that are specified in the ISA. So we're going to design a processor that looks like this. Okay? So you should start thinking about what is the clock cycle time determined by. We've seen this in lectures before, timing and verification, for example. How long does it take to the maximum combinational logic delay plus the setup time plus the hold time of the sequential logic? That's your clock cycle time. And that should be determined by what is the longest instruction to execute, right? What is the longest delay that you have over here? And the critical path, essentially this is determined by the critical path of the combinational logic plus the setup and hold times. What is the critical path of the combinational logic determined by? That basically depends on what you do in that cycle. And that is dependent on what you should do to specify the operation of an instruction, right? So the longest instruction that you need to execute determines how fast that combinational logic will be. Of course, what you do in that combinational logic matters. If you use a ripple carry adder, let me finish this and then we'll take a break. So depending on how you design the adder makes a big difference. So what is this architectural state over here? So just so that you know, this is the programmer visible state, right? You have memory, registers, and program counter. And instructions and programs specify how to transform the values of this programmer visible state. This is AS, all of it, and we transform it to AS prime. Okay, so this is probably a good place to take a break. Now we're going to delve into the design of a single cycle machine. Okay, so let's continue where we left off. If you remember, we were talking about a basic instruction processing engine, which looks like this. This is a single cycle machine. Now we're going to build this single cycle machine. And we're going to also see the disadvantages of it so that we can motivate multi-cycle machines. And then later we're going to look at the disadvantages of multi-cycle machines so that we motivate pipelining. And then we're going to look at disadvantages of just pipelining, and then we'll motivate out-of-order execution. So these lectures will build upon each other. Okay, this is the program visible state, and we already said this. Basically, actually, I'm going to give you the high-level disadvantages before we build the machines. So clearly, each instruction takes a single clock cycle and a single cycle machine. All state updates are made at the end of the instruction's execution. The big disadvantage is that the slowest instruction determines the cycle time, right? Because you need to implement every instruction a single cycle. If one instruction, let's say you're doing a floating point divide, a very complicated division operation, that takes a lot of time, for example, and that determines your clock cycle time now. Your maximum combinational logic delay is dictated by that. An add may be very quick, but you have only a single clock cycle to be able to execute every single instruction. So that's not good. So your clock frequency actually is lower in single cycle machines. That's why multi-cycle machines are nicer. You break instruction processing into multiple cycles and stages, and you still can do state updates during an instruction's execution, as long as you don't make them visible to the architectural state. Architectural state updates happen at the end of the instruction's execution. The advantage is now you can break things into smaller stages, maybe balanced stages, and the slowest stage determines the cycle time. There's a difference between slowest stage and slowest instruction. You have control over the stages. Of course, you have control over how fast you can implement an instruction, but you're limited because a division still is a division, right? It may take a long time. Whereas here, you can chop things into smaller stages, and each stage may be really fast, little combinational logic. You may have a lot of stages. And both single cycle and multi-cycle machines literally follow the von Neumann model at the microarchitecture level. Basically, it's a sequential. They don't move to the next instruction before they finish the previous instruction. You have to finish the current instruction so that you can move to the next. So now let's take a look at how we build these machines. Basically, we have a control unit, as you know, that processes the instruction step by step. And we know of this instruction cycle. There are 6 steps. We've already covered this, as you know. And you already know that not all instructions require all 6 steps. And this is the example that we've seen many times before. So if you look at a single cycle machine, all 6 phases of the instruction processing cycle take a single machine clock cycle to complete. Basically, if you go back to this, all of this happens in a single clock cycle for any instruction. Whereas in a multi-cycle machine, all 6 phases of the instruction processing cycle can take multiple machine clock cycles. In fact, each phase, fetch, for example, can take multiple clock cycles if you want. Evaluate address can take multiple clock cycles. So that's the view you should take. So think about this. Here, not everything happens in a single clock cycle. It may actually take, for some instructions, it may take 20 clock cycles to finish this. Right? Okay. So let's look at this in some other way also. Basically, what we're doing is transforming architectural state to architectural state prime when we execute an instruction. Essentially, that transformation is done by what's called the data path components, or functional units. Functional units are part of data path components. These are units that operate on the data. Those units need to be told what to do to the data. So you have a clear distinction between data path and control. So basically, an instruction processing engine fundamentally consists of these 2 components. Data path is the hardware elements that deal with and transform data signals. These consist of the functional units that operate on the data, like the arithmetic logic unit, ALU, or hardware structures that enable the flow of data to the functional units and into the registers, like wires and muxes, and storage units that store data, the registers, as we will see, as you've seen also before. On the other hand, control is very different. Control consists of the hardware components that determine the control signals. Basically, signals that specify what the data path elements should do to the data. So a control signal of a mux specifies which input should be passed through the multiplexer. The control signal of the ALU specifies what function should the ALU perform at this point in time. Okay, so we will see this distinction between control and data path. That's how we were going to build our single cycle machine. Always keep in mind you have data path components and you have control components. You may use few data path components and you may control them differently for different instructions. So different instructions may use the same data path components, but your control signals will be different in terms of how you use those data path components. So you can actually build a very simple machine with very simple data path components and control it in a nice way so that it can be powerful. Okay, So if you think about the single cycle machine, the control and data is a little bit different between these two machine types. Basically, control signals in a single cycle machine are generated in the same clock cycle as the one during which data signals are operated on. Basically, control signals need to be generated during part of the clock cycle, and then you use those control signals to control the data path elements. So essentially, everything related to instruction processing happens in one clock cycle. So it's serialized. You have to generate the control signals, and then the data needs to flow based on those control signals. In a multi-cycle machine, you don't have this constraint. That's another beauty of a multi-cycle machine. Basically, you can generate the control signals that you need in the next clock cycle during the current clock cycle. While you're doing something right now, you generate the control signals for the next clock cycle, which means that you can overlap the latency of control processing with the data path operation. So this way you can get multiple parallelism across clock cycles. Okay, we will see this more clearly when we talk about multi-cycle machines. And if you read Appendix C, this should be relatively clear by now. Okay, so there are many ways of designing data path and control. Let's take a look at some of them. So we have single cycle, multi-cycle pipelines. We have single bus versus multi-bus. So if you remember the LC3, you have a single bus design. But actually, in real machines, you have multiple buses, as we will see. You can have hardwired controlled or microprogrammed, micro-coded control. We will see that later. What does this mean? Basically, hardwired means control signals are generated by combinational logic, or you could access a memory structure to get the control signals. Basically, you have this instruction that you're decoding. You want to get the control signals for the next clock cycle or this clock cycle. Do you have a decoder that's combinational that generates the control signals, or do you access a memory location to get the control signals? And control signals and the structure depend on the data path design, as we will see in a little bit. We're going to design the data path and the control. But before we jump into that, let's do a little bit performance analysis so that you can appreciate this a little bit more. So what does performance mean? Basically, performance is how long does it take to execute a program? Let's assume we're concerned with just one program. One program consists of many instructions. Essentially, you need to calculate the time it takes to execute all of those instructions. So to be able to get there, we want to understand how long it takes to execute a single instruction. So execution time of a single instruction is calculated like this. Basically, how many cycles does it take to execute the instruction times the clock cycle time? This makes sense, of course, right? Basically, you have an instruction, let's say an add. You know how many cycles it will take, and you know how long each clock cycle is. Each clock cycle is 10 nanoseconds. If the add takes 3 clock cycles, it takes 30 nanoseconds to execute the add. Each clock cycle is 10 nanoseconds. The multiply takes 50 clock cycles. It takes 500 clock cycles to execute the multiply. Okay, so the execution time of a program is basically you do this for every instruction. You figure out how long each instruction takes, and you sum those times up. Makes sense, right? This assuming you don't overlap the execution of the instructions clearly. But this equation, we're going to use it when we overlap, but we're going to look at this in a different way. So basically, this is the iron law of performance analysis. You have number of instructions times the average cycle per instruction times the clock cycle time. This is another way of thinking about this. You can average the cycles per instruction. And this is how many instructions you have in the program, average cycles per instruction for that, and the clock cycle time. Okay. So let's take a look at, we're going to get back to this. Let's take a look at the single cycle microarchitecture performance with this equation. What does single cycle microarchitecture mean? It means cycles per instruction is always 1. It doesn't matter what instruction you're executing. You take only 1 cycle. But the clock cycle time is long, meaning that you actually need to ensure that the clock cycle time is long enough to execute the longest possible instruction. Multi-cycle microarchitecture, on the other hand, cycles per instruction is different for each instruction, and you can make the clock cycle time short because you're designing how long it takes to execute each stage, right? And hopefully, you can make the average CPI small also. For example, if you're executing adds most of the time, add instructions most of the time, add instruction may take only 3 cycles, right? Maybe a division takes 50 cycles, yes, but you're not executing that very often. So your average CPI is closer to 3 as opposed to 50. And this way your CPI is small, your clock cycle time is also small, hopefully, short, and your number of instructions doesn't change between single cycle and multi-cycle because it's the same program. So basically, the advantage of multi-cycle, as we will see, is you have 2 degrees of freedom to optimize independently. You can optimize the clock cycle time by changing how long your stages are, and you can optimize how many cycles it takes to execute each instruction for different instructions. Okay, so now you know the basics of performance analysis, yes?
Would that mean that I chop up an instruction to multiple parts and then execute them over multiple clock cycles?
Exactly, yeah.
Wouldn't they create overhead because I have to store intermediate results?
Exactly, yes. That's the overhead that we will also see. So basically, that's your colleague pointed out that there's an overhead, yes, because you need to store the intermediate results. And based on the timing and verification lecture, you know that whenever you need to store something into a flip-flop, there's additional delays. And also there's overhead in terms of additional area because you need to have flip-flops to store these intermediate results. So it's going to be more expensive to build this multi-cycle machine, but it's going to be faster. And you will see that after multi-cycle comes pipelining, it's going to be even more expensive to do the pipelining. Okay, so let's take a closer look into the single-cycle microarchitecture. This is essentially the abstract view. Now we're going to design what goes into the combinational logic over here. And I'm going to give you an example that's not from your books, but that's essentially similar. You will see how similar everything is. It's really important for you to see the differences because the real world is going to be different from your book and maybe actually very different from your book. But as long as you understand the fundamentals, it's going to be similar. So we're going to start with the state elements. This is our program counter. This is our register file. This is our instruction memory, and this is our data memory. So you can see, because it's a single cycle machine, there's no program counter load. Every clock cycle you load the program counter. Because every clock cycle you process a different instruction, right? So automatically, at the positive edge or negative edge of the clock, you load the program counter. There's a control signal over here. Control signals are orange. This is basically the control signal for register write. Are you writing to a register? And if you're writing to a register, this write register ID specifies which register you're writing to. And these are the IDs for the read registers. If you know MIPS, so it takes 5 bits to specify registers. And then this is the data that's to be written to the register you're writing to. And these are the 2 read ports. Basically, you can read 2 registers in the same clock cycle. You provide an instruction address to instruction memory, you get the instruction out. You provide an address to memory. You can read the data, assuming this signal is set, memread. So if you want to read the memory, you set the memread to 1 and memwrite to 0. If you want to write to memory, you set memwrite to 1, memread to 0, give an address, give a data, and read data is undefined at that point. Basically, you're not reading it according to this definition. So basically, we start with these building blocks that somebody has defined. And your book actually has similar building blocks. So these are the state elements that we have. You have the program counter, you have the instruction memory, and I've already defined this. You can read this on your own. The register file, it has 32 elements in MIPS. 32-bit register file has 2 read ports and 1 write port. Here you have the write enable control signal. And data memory has a single read-write port. And I think we've already discussed this. Basically, if the write enable is 1, the data memory automatically takes the write data and writes it into the address. If the write enable is 0, it reads the address A onto read. But in this case, I'm going to also have a signal saying memread to explicitly specify that. What happened there? Okay. Okay. So for now, we will very quickly, we will assume combinational leads. Don't get hung up on this that much, but basically output of the, because we're dealing with a single clock cycle, output of the read data port is combinational function of the register file contents and the corresponding read select port. And we have synchronous writes. Basically, the selected register is updated on the positive edge of the clock transition when write enable is asserted. This is as you expected, right? So you cannot affect the read output between clock edges. You have the read data available for the clock cycle. You have the data that you've written that gets latched at the beginning of the clock cycle, and you have that available. So we're going to assume single cycle synchronous memory. So basically, we're going to be able to write to memory in a single cycle. So if this takes a long time, again, your clock cycle is determined by this, right? So that's one of the disadvantages of the single cycle machines also. So you could also have a memory that tells when the data is ready, and design your finite state machine based on that, but let's not go into that right now, and we're going to talk about that later. Okay, so this is our basic data path. I'm going to actually connect these components, and this is going to be our data path. So we have 5 generic steps. This book is not required, but it's very similar to your book. Instruction fetch, instruction decode. You will see all of this is going to be exactly the same, actually, almost. The control signal names will be slightly different. So instruction fetch is where you fetch the instruction. Okay, let me do it over here. You input the program counter into the address of the instruction memory, and you get the instruction out. And then you have a decode stage where you decode the instruction, figure out what it's supposed to do, and then you fetch the operands from the register file, and then you execute the instruction or evaluate the memory address. We'll call this the execute AG part of the data path. And then once you have the address, you may actually use that to fetch an operand from data memory. And then you get the value from the data memory and write it back into the register file, assuming this load. If it's a store, then this store needs to happen over here. So essentially, this is your data path for many different instructions. You can use this data path, and we're going to form this data path a little bit more rigorously. This is just a picture right now. So this is what's to come. Hopefully at the end of this lecture, although I'm not sure if we're going to finish by the end of this lecture. We may be able to. This looks complicated right now, right? But it's really not complicated once you figure out how each component is. And the picture in your book is actually very similar to this. Okay, so let's start. So this is actually the picture in your book. If you look over here, glimpse a little bit, it's very similar. Okay, so let's start building this data path from the ground up. So somebody gave you an ISA, instruction set architecture. How do you design a machine that operates, that basically obeys that instruction set architecture? So somebody needs to give you the instructions clearly. So we start with the ALU instructions first, arithmetic and logical instructions. And the data path for arithmetic and logical instructions are essentially similar. So remember, in MIPS, we have R-type ALU instructions. We're going to build the data path for that first. R-type means you have 3 register operands, these 3. RS, RT, the result goes into RD. And this is basically, the semantics is that if the instruction is this, the opcode is this, and the function is specified like this, you do the add. Basically, what does that mean? You take, you access the general purpose register file with the indicator RS, get the data, add to it, and then access the general purpose register file with the register ID RT, add those 2 values that you get from the register file, and update the register file at location specified by RD. And then you increment program counter by 4. Nothing surprising here. And this is the data path you need to be able to do that, basically. Basically, you translate this semantics into combinational state update logic using the elements that I've introduced earlier. So what does that mean? Let's do this PC plus 4 first. During this cycle, what needs to happen? These 2 things need to happen concurrently at the same time. That's what add specifies. So we basically need to take PC, add 4 to it, and write the result back into the PC at the end of the clock cycle. That's one part of what needs to happen, and you need to have the data path component to do that. Also, you need to read instruction memory, fetch the instruction. That now you've got the instruction over here. Now the decode of the instruction, assume that we have an add. What does that mean? You need to be able to read the registers, register 1 and register 2, which brings you the data in the register file. And then the ALU operation needs to be an add. So you need, the control logic needs to specify that this is an add. This is a control signal, as you see, it's orange. And the data flows this way during the clock cycle. You read the registers, ALU specified add, which means that you've done the addition. The result needs to be written back into the register file as specified by the write register, and you need to assert the reg write signal. So reg write control signal needs to be set to 1. So these are the data path elements. You need 2 control signals, reg write and ALU operation, to be able to implement the add. Makes sense, right? Very simple. Okay, so here, now actually we've implemented add, but we could implement other things. As any R-type MIPS operation that goes through the ALU is implemented this way. Because you read 2 registers, you write 1 destination. The only difference is what the ALU operation is. right? For example, if you're doing an OR, the ALU operation function is 0, 0, 1. If you're doing a bitwise AND, it's different. If you're doing an add, the ALU operation is this. And you might be doing other stuff also, depending on what your ISA specifies, right? So basically, this is the control signal for the ALU. And depending on what the instruction opcode, or at the bottom, that funct part, remember the function part in MIPS is, you set the ALU's control signals accordingly. Okay, we're done with R-type ALU instructions. Now we have some basic data path. Now we're going to build on it. How do you do I-type? What is I-type? You don't have 3 register operands, you have 2 register operands and 1 immediate. One register operand is a source, the other register operand is a destination, and you basically, what the instruction specifies is clearly you increment the PC, you take the source register, RS, add it to a sign extended immediate that comes from the bottom 16 bits of the instruction, and store the result into the general purpose register specified by RT in this case. So it's the location where RT comes is a little bit different from the bits that are specified. If you go back, this RD is essentially these bits, bits 11 through 15 over here, whereas these are bits 16 through 21. Okay, so we're going to add a MUX in the data path to be able to execute this in a similar data path. So let's take a look at that. Okay, so this is, we start with the data path with R-type instruction. Now we're going to add I-type on top of this. PC plus 4 stays the same. You fetch the instruction. Now what does I-type do? You need to read one of the source registers, add to it the bottom 16 bits of the instruction, sign extended to 32 bits. So now your ALU operation needs to be an add still. Well, in this case, it's an add, immediate. The source is one of the register operands, and the other source is a little bit different now. It doesn't come from the register file, it comes from the sign extend immediate that we added to the data path so that we can implement this instruction. So what do? Well, we add muxes. There are actually 2 differences. Let's take a look at this one first. Basically, you have a mux that selects between the output of the second read port of the register file and the sign extended immediate coming from the instruction. How do you decide which one you actually choose? Basically, you decide if the instruction is I-type. If the instruction is I-type, you choose the bottom input to the mux because you want to add the immediate to the first source operand coming from the register file. If the instructions are type, you want to add 2 registers, so you choose this one. So this is the control signal we have. It's called is I-type, or ALU source. So that's part of the data path elements. So when you add a data path element, you also add a control signal over here to choose which part of the data path elements the data should flow through so that you can execute different instructions. Make sense? We could have added a completely separate ALU also, right? For just I-type versus R-type, but that would be not so good probably, right? Because that's a lot of overhead. Instead, we use the same ALU and we decide which input should go to the second operand of the ALU. Okay, that's one. We also need to add this mux. The reason, as I said earlier, is destination register of I-type instructions comes from bits 15 through 11. No, the other way. The destination register of R-type instructions comes from bits 15 through 11, whereas the I-type comes from bits 20 through 16. So if the instruction is I-type, you choose bits 20 through 16. Otherwise, you choose bits 15 through 11 as the right register identifier. That's specified by the ISA. We don't have control over here. Somebody specified the ISA. This way, the destination register here is RT, bits 16 through 21. If you go back to R-type, the destination register here is bits 11 through 15. And if we want to use the same data path elements, we have to add these muxes and control them appropriately. So if we're executing an I-type operation, we set these as I-type to 1, and the data path elements are controlled accordingly so that you do the add immediate. And you could also do some other immediate operation based on the ALU operation. Okay? So LC3 was similar. If you, this is just to jog your memory. We've actually seen something like this before. If you look at LC3, this is add with 1 literal, add immediate. It has very similar control logic as you can see over here. This is, you have a source register coming from here. You have another source register coming from here. and the bit inside the instruction that distinguishes between R-type and I-type in LC3 selects whether you choose the second source register coming from the register file, or you choose the sign extended immediate coming from the instruction. And this MUX is essentially very similar to this MUX over here, because the ISAs have add, register add, and register plus immediate adds. Okay, so hopefully you'll see that there's no magic here. It's very, the way you implement an add immediate and add instruction with a simple data path with minimal elements is very similar across different ISAs. But the microarchitecture is slightly different, as you can see, based on the ISA specification. Okay, so now we're done with R-type and I-type arithmetic and logical instructions. Even though I didn't talk about logical, you can imagine that shifts are implemented in a similar way, right? Let's take a look at extending this data path with data movement instructions. So we're going to add loads now. This is load word in MIPS. Its specification is like this. You basically increment the PC. You calculate the effective address by sign extending this offset and adding it to the value of the base register specified by this. And then you access memory with this effective address. Ignore this translate for now. In real MIPS, you actually have a translation, which we will talk about at the end of the course. But basically, you take this effective address and access memory and write the result back into general purpose register indicated by this RT. So it's actually very similar to an I-type operation, right? This is immediate, RT is destination, RS is source. It's actually very similar, except the opcode is different, right? Okay, so we're going to use the same data path to incorporate load word. So what do we need over here? Well, PC plus 4 remains the same. Now, essentially, the instruction needs to read the register, base register, specified by RS. So this is the first register that you get. Add to it a sign extended immediate coming from the bottom 15 bits. It's very similar to add immediate. So we do an add over here. So we don't need to add anything, actually, because we already did this for add immediate. Load just happens to calculate effective address the same way add immediate adds a register to assign extend immediate. So we didn't add anything over here. But we need to be able to access memory in this case. So the result of the ALU, which is the effective address, needs to get connected to the address over here. And we need to ensure that we're not writing to memory. So this control signal needs to be set to 0. We need to ensure that we're reading memory. This control signal needs to be set to 1. And the read data needs to get connected to this write data over here, such that the data that comes out of memory at effective address that's calculated by here is written into the register file to the register that's specified by bits 20 through 16 in the instruction. And we already did that for, at least we did, we added this MUX for I-type instruction. Load word is essentially an I-type instruction. So you set the control signal similarly over here. And we need to ensure the register is written, of course, we set the register write signal to 1. That's true for all instructions where you write into a register. Makes sense, right? So that's our load word. Basically, all we needed to do on top of add immediate is access memory using the ALU result and write the data coming out of memory over here. But of course, it's not that simple because we need to add some MUXes now, right? Because remember, add immediate needs to write the data coming from the ALU result directly into the register file. Load word needs to get the data from the memory and write it into the destination register. To be able to do both, execute both in the same machine, you need to add a MUX, which we will see later. Store word does, let's look at store word first. Store word is actually a bit easier because it calculates the address in a very similar way to load word and writes the result into the memory with that effective address. Well, what was the result? Result comes from the register file specified by RT. Right. So to be able to execute store word, we calculate the effective address in the same way we do for load word. So now you have the effective address over here. Now where does the data come from? The data comes from essentially this register over here. So let me give you the full data path. Basically, I'm constructing it as I go, but the data comes from this register over here. So it's really the second port. So the first register base is this one. You add to it sign extend immediate to calculate the effective address. And the data of store word comes from the second register port, which is essentially RT over here. Okay? So use that as a source register in store word. And you set memory write signal to 1, memory read signal to 0, so that you write to memory, and you ensure that the destination register is not written. Right? Register write signal is 0. Because we're doing a store, and store doesn't change a register. It needs to write to memory. Make sense? So this is the complete data path that can execute everything we've discussed so far. So, yeah, this is actually not the, this is the load store data path. This is the load store plus add data path. So this doesn't have the mux over here. Basically, this is what we can do, stores and loads. But if you remember, I said that you need a mux over here. So the add immediate, or add writes its result from the ALU to the register file. A load writes its result from the memory to the register file. And basically, you need to pick which one to do depending on which instruction you're executing. So you need another data path element, this mux. And you need to control the data path element accordingly depending on which instruction you're executing. In this case, if we're executing a load, is load, you pick this mux is controlled, this is true, and this mux selects the signal coming out of the memory so that it can be transferred to the register file. If it's not a load, then the mux selects the result coming out of the ALU output and writes it and sends it to the register file. And you can see that these are the control signals. Basically, this is controlled by the I type. If the instruction is an I type, this mux selects this signal over here, otherwise this signal. If the instruction is an I type, you select the sign extended immediate over here. If the instruction is store, you write to memory. If the instruction is a load, you read from memory. If the instruction is a load, you get the data coming out of this port of the mux. And this register write turns out to be, if it's not a store, you're writing to a register, assuming we just have the instructions we've seen so far. Okay, so basically you construct a data path that can actually execute arithmetic and logical operations plus memory access operations. Now let's add control flow instruction on top of this. So we're going to look at the simple jump instruction. This is going to complicate some other parts of the machine now. So what does jump say? Jump is simple. Basically, you calculate the target address by concatenating top 4 bits of the PC with the immediate value and shifting it by left by 2, basically adding zeros at the bottom. And then you basically set the target, set the PC to that target address. So it's actually not that bad. We can use exactly the same data path. We're going to complicate this part because we're not going to touch anything in this data path. Of course, we should do no harm. No harm meaning clearly jump doesn't write to a register or write from memory, write to memory, right? So we should not write to a register. We should not write to memory. That's no harm. Because when you execute a jump instruction, you don't expect that to happen. So clearly, basically, we're not going to write to a register. We're not going to write to memory. I guess we could read from memory as long as we're not going to do anything with it, but why read from memory if it's not necessary? So this could potentially be an X. And we don't care what happens over here because we're not going to use any of these results. We're not going to write to a register or write to memory. So these are don't cares. But we need to do is add some other data path elements over here. So what are those? Basically, we need to take the bottom, let me go back to the instruction definition, bottom 26 bits of the instruction, concatenate it with the top 4 bits of the program counter, shift it left by 2, and then send it to, load it into the PC. So if the instruction, and then we need to add this mux. So if the instruction is a jump, this is the data path elements that happens. You basically take the top 4 bits of the PC, use the PC to access the instruction memory to get the instruction. You get the bottom 26 bits of the instruction, concatenate them, write the result into the PC. That's how you update the program counter with a jump. If the instruction is not a jump, program counter is updated by PC plus 4, as you can see. Now we've added the data path elements to be able to execute both jumps and not jumps. And if this is all of the control signals, but you need to set the control signals to be able to execute that jump correctly. Okay, it's fun, right? But clearly, as we add more instructions, the machine is getting more complicated. Okay, so there are other instructions like jump register, jump and link. Jump register, for example, what it does is it calculates the address by reading a register and putting the register into the program counter. So that's jump register for you. So basically you need to add the data path elements, the wires and the mux input, so that you could take the register that you're reading, specified by the instruction bits, and place it into the program counter. So that's the data path component that you need. Now this becomes more complicated. It cannot be just is jump. Now this is a 3-input mux. You have 2 bits to select. So if you're executing a jump register, this should be the input that you select. So now you add more control signals to be able to do that. There's also other stuff that happens with jump and link, which we didn't discuss, but you can, so basically jump and link means that you jump to a register and you save the program counter in some other register. Okay? So if you want to that's jump and link register, sorry. There's jump and link actually, you get the address from the PC plus concatenation and then you save the register, you save the PC to a register. Jump and link register is actually more complicated. You jump to a register and then you basically save the PC to another register. So you need to add the data path components to be able to execute that. I'm not going to go through that right now. So these are the other jumps over here basically. Okay. So maybe I was wrong, let me see. So these are the other jumps in MIPS. So this is what we jump and link. Yeah, actually, that's essentially what I said. Jump and link register, this is the most complicated one. You save the PC plus 4 to a register, and you use the source register to change the PC. So you need to be able to provide the data path elements to be able to do that. That will complicate the different parts of the machine. So if you want to learn more about MIPS, there's a MIPS cheat sheet, which we can update. Let's take a look at conditional branches. This is going to complicate things even more. But we need to be able to execute these, so we need to be able to add data path elements as well as control signals to be able to do that. So what is, you remember branch if equal. What does this instruction do? It tests whether the data value in RS is equal to RT. And if that's the case, it basically changes the program counter to a PC plus 4 plus sign extended immediate, shifted by 2. Okay? So if the registers are equal, PC gets the target address that's computed like this. Otherwise, the PC just goes to the next sequential instruction. So we need to be able to do this. So I'm not going to give you this in this slide. First of all, whenever you implement this, you should ensure that you don't do any harm. This doesn't write into any register, write to memory. That's why memory is omitted over here. To be able to implement this, you need to actually add more data path elements so that you can subtract the source register from the destination register, and then you get a value. And then you need to compare if that value is equal to 0. So there's some logic that needs to be added if that value is equal to 0. Now if that value is equal to 0, then you take the target address. So where is that target address? Well, we need to add some more data path elements to actually calculate the target address. So how do we calculate the target address? Basically that's PC plus sign extend immediate shifted left by 2. So this is our sign extend immediate. We used it actually as an ALU input before, but we didn't shift it left by 2. Now we shift it left by 2. And then we get PC plus 4, which is here actually. And add to this sign extend immediate shifted left by 2. That's the target address we have. So that needs to be input into the program counter mux over here. So this mux is getting more complicated, as you can see, to be able to handle different types of branches. Now that's not enough. Now the input signal to this mux is dependent on whether the source register is equal to whether the one source register is equal to the other source register, right? So you need to actually do some logic over here. If the 2 source registers are equal, if the subtraction gives you 0, then you need to select this target address. Otherwise, the target address should be PC plus 4. So this PC source signal is actually now controlled by not just the instruction, but something that's happening in the data path, the result of the ALU. So that's why this is more complicated. Control signal is not just a function of the instruction bits, it's also a function of whether register 1 is equal to register 2, right? Okay. So I'm going to skip the delayed branch. So basically, if you actually include all of those, this is what happens when we put it all together. So let me go over the conditional branch case again. I already described it to you, but basically what happens is, if you have a conditional branch, you read the source register 1, you read source register 2, this mux needs to select the source register 2, the ALU operation needs to be subtract, which is part of the ALU control over here, and you subtract source register 1 from source register 2, and the result is branch condition over here. It's not as simple because you have different types of branches also. That's why you have a branch condition. There's a branch less than or equal, for example. So if the branch condition is true, and if this is a branch instruction, this becomes a 1. And this controls this mux over here. This mux selects this ALU result, which is PC plus 4 over here, plus a shifted left by 2, sign extended, immediate coming from the instruction. That's essentially the target address of the conditional branch. So this basically is the mux that controls whether selecting between the target address versus PC plus 4. And that is dependent on the branch condition, as you can see over here. And then there's another mux that goes into the program counter. That's the 4-input mux I showed you in the earlier slide. If it's not a jump, you select this. Basically, if it's not a jump, you select either PC plus 4 or the target address of the conditional branch, and that gets fed into the program counter. So that's how you can execute a conditional branch. So I didn't go through all of the instructions clearly over here, but you need to be able to do what we essentially did for every single instruction specified by the ISA to be able to build a MIPS processor. And once you're done, you need to ensure that it's correct, of course, and the control logic gives you the right control bits. Let's talk about the control logic relatively quickly. But I've given you an example of the control logic, but we should also go through it. Essentially, what we've done is a single cycle hardwired control. We're determining the control signals as a combinational function of the instruction that we're executing, right? And we've gone through R-type, I-type, and jump-type instructions, J-type instructions. So these are the things that we've considered so far. I didn't talk about these, but actually the data path that is here covers that. I'm not going to go through all of them, but this is how you can determine the control signals. Let's take a look at an easy one, which is register write. So register write means that should you enable the reg write signal into the register file? Are you writing to a destination register? How can you generate this control signal with combinational logic? Well, this actually shows you how you do it. Basically, you set the signal if the opcode is not store word, if the opcode is not a branch, if the opcode is not a jump, if the opcode is not a jump register. Basically, everything else needs to write to a register. Basically, you design combinational logic that sets this control signal to a 1 for instructions that write to a destination register. Otherwise, this signal should be set to 0. And this is the combinational logic that leads to that. Mem to reg, this is the mux that we added coming out of the memory port and coming out of the ALU result. Do you select the ALU result to write into the register file, or do you select the memory output to write into a register? Well, you need to think when you're designing, who writes the memory output into a register? Only the load instruction. So if the opcode is a load word, then the mem to reg signal is set to 1. Otherwise, it's set to 0. So if you go back to this picture over here, actually the picture that, yeah, this is the mem to reg mux over here. One input comes from the ALU, and the other comes from here. Okay, so this is a good place to stop. We're going to continue with control, and we're going to go to multi-cycle tomorrow. See you tomorrow.